Okay, cool. So last time we went over the rules of aromaticity and everything, and we did a lot of examples here. And so today we're going to focus more on the heteroatom rules and then the molecular orbital theory stuff. So we did the first couple heteroatom rules, which was the single bonded ones and the double bonded ones. We also talked about how boron is an exception to that rule because it is always sp2 and it donates 0 electrons. And the last rule that we didn't get to talk about is, what if we have multiple heteroatoms? And I was very sad because the first question he opened class up with was 2 heteroatoms. And I was like, why couldn't you do something we covered, bro? Like, but it's okay, we're gonna cover it now. So if you have multiple heteroatoms, there's like 2 categories, I guess, that you can go under. So they can either be both single bonded, and if they're both single bonded, the same sp2 versus sp3 rules apply, but now they both have to have the same hybridization. So they both must have same hybridization. So either they're both sp2 or they're both sp3. And if they are sp2, they each donate 2 electrons, aka 1 lone pair. And then we can also say, I'm not going to do every single possible combination because really the only 2 that'll pop up is either they're both single bonded or one is single bonded. Yes. Yes, exactly. So they're each going to donate 2 electrons, aka 1 lone pair. No, each is going to donate 2. Total is 4, exactly. And then if one is single bonded, one is double bonded, then this whole, like, they have to be the same rule doesn't apply because the double bonded one, wow, okay, double bonded one must be sp2 and donates 1 single electron. And then the single bonded one can choose 2 or sp3. So it does not have to be the same hybridization, but if they're both single bonded, then it does have to be the same hybridization. Thought I saw a hand. Did someone have... So if it's double bonded and it's sp2, it can only donate 1 electron because it's donating the 1 single electron that's part of the double bond. So I can show you what that looks like because I have it drawn out. I'm just going to give a second or 2. That. Alrighty, so if you need me to go back to this, I can, but I just want to go up here for 1 more second. Alrighty, so for the sp2 thing that we talked about, when we have a nitrogen, usually it's going to be a nitrogen, but it could be an oxygen as well if you do it right. So this guy has its lone pair of electrons right here, but it has this p orbital that is attached to a double bond, right? So that p orbital that's in a double bond is the only thing that's donating into your aromatic ring. So this one electron is the only thing being donated, and this whole orbital is in a different plane, so it can't donate that lone pair. Does that sort of kind of make sense? Okay, so think about it this way. So in order for it to be like delocalized, because that's the whole point of aromaticity, right? All the electrons are being delocalized all around the ring. So in order for those electrons to be delocalized, all of those orbitals have to be pointing in the same direction. That's how they become delocalized. So they can only trade electrons if they're pointed in the same direction. And when we have, I didn't draw it out, did I? Okay, I kind of drew it out. So when we have heteroatoms in a ring, and we were talking about sp2 versus sp3, like when does it want to be each of those things, we kind of talked about how they can choose to have their orbitals aligned with the rest of the p orbitals, or they can choose to put them on a different plane, like I drew here, right? So the nitrogen in this case would want to point up instead of to the side, because then these electrons can donate to these blue orbitals. But in this case, they can't donate because these are like laying flat and these ones are going straight up and down. If it's double bonded into the ring, it doesn't have a choice anymore because this orbital is part of a double bond. So let me just draw out. This essentially just means that it's double bonded. So this is stuck. It can't move this orbital whatsoever. And then this orbital is stuck being flat. And since it's flat, it can't donate to the ones that are standing upright. Does that make a little tiny bit? Or is it still like? Yeah, you can, yeah. This is one of those things where if you don't see it, you're fine memorizing it. I want you to see it, but like it just doesn't happen for some people, and that's okay. All right, so let's do the rule that we were just talking about. So let's do this one right here. So how many electrons max can each oxygen donate? 2. Okay, so this is like a trick here. You should get rid of the second lone pair on each oxygen, because each one can only donate up to 1 lone pair, right? Okay, so we also know that the oxygens, since there's 2 of them and they're both single bonded, they have to have the same hybridization. So either they can both be sp3, and we would get what? If it's an sp3 atom. Would it be aromatic, anti-aromatic, or non-aromatic? Ooh, it's going to be non-aromatic, because sp3 breaks which rule? Yes, breaks the conjugated rule. Can't see that. So it breaks the conjugated rule. So we're just going through the 2 options. So either it could be sp2 or it could be sp3. So since sp3 is always non-aromatic, that's just the one I write out first. All right, so if they were both sp2, they both have to donate 2 electrons each, right? So we would get a total of 2, 4, 6, 8 pi electrons. So 8, is that the 4n rule or the 4n plus 2? 4n, and is that aromatic or anti-aromatic? Anti, cool. Any questions on how I counted up those electrons or anything? Yes? Okay, so let's go through it right quick. So each of the double bonds is 2 electrons. So we count 2, 4. And then if the 2 oxygens were both sp2, they will each donate 1 lone pair, aka 2 single electrons. So we get 2, 4, 6. Yep. If it's single bonded, it's always 2 per atom. Double bond, it's always just 1. All right, so what's more favorable, sp2 being anti or sp3 being non-aromatic? sp3, yes. So both of these guys are sp3. And how many electrons do they donate? 0, yes. And since this guy is right next door, let's do those 2 while you guys continue writing. So if it's double bonded outside of the ring, is it sp2 or sp3? sp2. And how many electrons does it donate? 0. Cool. So we're just going to pretend this is a carbocation, just because I don't like looking at complicated things, right? And so now we are cyclic, planar, fully conjugated. Yay. How many pi electrons do we have? 6, right, because there's 2 per double bond. And is that 4n or 4n plus 2? 4n plus 2, cool. So this guy is aromatic. Yay. And then what about the boron one? What's the hybridization of boron? It's always sp2. Cool. And then how many electrons? 0 electrons. Cool. So this one is also like a carbocation. So we're going to have the same exact answer as before. Or before meaning this guy. So it is also 6 pi electrons. Going to be aromatic. I apologize. For this one, you mean? So you could do it either 1 per each atom of the double bond, or you can say 2 per double bond. Whichever one's easier, because some people don't like the 1 per atom per double bond. But yes, okay. So then let's do this guy. Right? It looks very ugly. Oh yes, what's up? No, in this class, that's never going to happen. So if it's double bonded, it only gives 1. But good question. Alrighty, so for this one, there's a lot of stuff going on. So let's look at this first, right? We just talked about this one, and we're going to pretend this one is a what? Carbocation, cool, because it's a heteroatom, but it's double bonded outside the ring. So we're just going to pretend it's not even there, and we're going to give this carbon a plus charge. Cool. Next thing, we have 2 single bonded heteroatoms here. So they could either be sp3, which means what? Non-aromatic, cool. Or they could both be sp2. And this time he didn't draw any electrons. So how many electrons max can these guys give you each? 2. So I'm just going to draw 2 electrons here. Cool. And so now if they were both sp2, how many electrons would we have in this molecule? 8 again, yes. And so that would mean it's what? Aromatic or anti? Anti. So now again, we're stuck between anti-aromatic and non-aromatic. And you guys told me last time we would choose non-aromatic. And so this turns out to be like almost the same case, right? The only difference is it's a bigger ring and they added another heteroatom just to confuse you. But remember, if it's double bonded outside the ring, just get rid of it and pretend it's a carbocation. lot of words. Any questions on that? Alrighty. So I'll leave this up for another second, and then I'll move on to a spicy one where they're double bonded. There we go. Sorry for all the like zooming in and out. I feel like I'm giving people motion sickness. All right, so we have cyclic, planar, and that is a carbocation, so it's sp2. Cool. And we have two heteroatoms, but now one of them is single bonded and one of them is double bonded. So do they have to have the same hybridization now? No. Cool. So this nitrogen has to be what? Yes, so it has to be sp2, since it's double bonded, but the oxygen gets to choose. So we're going to say the oxygen can either be sp2 or sp3. If it's sp3, it's always what? Non-aromatic. Cool. All right, and then in this case, if it's sp2, it can donate up to one lone pair. How many total pi electrons would we have? 6. Cool, because again, this nitrogen is essentially just like another carbon. It's just donating one single electron. So we would have a total of 6. And would that be aromatic or anti-aromatic? Aromatic. Cool. So now, what would we choose? sp2 or sp3? sp2. Cool. So it's very important that you note now this whole atom, or excuse me, this whole molecule is going to be aromatic. This nitrogen is sp2 hybridized. This oxygen is sp2 hybridized. Total, we have 6 pi electrons. Cool? All right. Let's do one of the big rings because I don't remember if we got to do that last time. So, what was the rule I told you guys about planar molecules? Yes, so if it's less than 8 members, we're going to assume it's planar. But if it's 8 members or more, we have to actually take this planar thing into account. So this is an 8-membered ring. And once you reach 8 members, this guy has a lot of ring strain. So the angles in these bonds are like not very stable. It doesn't want to stay flat on the page. Instead, it wants to bend out of the plane and do this almost like boat structure, kind of like the chair conformations we had for cyclohexanes. So it wants to do that. But we know if it's not planar, can it be aromatic? No. So it has to be what automatically? Yes. So if it were to bend out of the plane, it would be non-aromatic. But actually, this ring can decide what it wants to do. So it could either like force itself to stay on the plane, or it can bend out of the plane. If it were to stay on the plane, in this case, how many pi electrons would we have? 8. So would that be aromatic or would that be anti-aromatic? All right, so in this case, this ring is super, super unstable because of all the ring strain, and it's also going to be anti-aromatic if it stays on the plane. Does it want to do that? No, because that's super unfavorable. Instead of suffering, it's just going to bend out of the plane, and it will become non-aromatic. Yep, but that's only for 8 members or more. So if it's a ring that's this size or bigger, not for the smaller one. Yes. So yes, you could think of it that way, but it's not necessarily just resonance. It's also something called hyperconjugation. So just know that that term is there, but you don't have to know too much about it. Yeah, it's kind of like, if you think about it like anions, right? So if a carbon is a negative charge, instead of donating one electron, like you were saying for the double bond, it donates two, right? But in that case, you don't have a choice. So it's almost like an anion, but it can choose to act either like an anion or not. That might not make it any better, so I hope that didn't just confuse. That's an okay answer. Okay. Let's keep talking about it, and then if you can ask me again if you have like another question or. Let's do right quick. This one is also an 8-membered ring. Yes, it is. Okay. I just had to make sure because it like looked weird. So this is another 8-membered ring. So let's go through it. A ketone. What are we gonna pretend that's like? Cation. Cool. So we're just gonna get rid of that. Cool. Get rid of that. Cool. So the way it's drawn, it's cyclic and fully conjugated, but we have to figure out whether or not it's planar. So if it's planar, we have to count the electrons. If it's non-planar, it automatically becomes what? Non-aromatic. Cool. So count up the electrons for me, please. 6. Awesome. So we have 6 pi electrons, which would make it aromatic. Awesome. So in this case, this guy is like, all right, well, I can suffer a little bit and have ring strength, and I get aromaticity, which is awesome. Or I can bend out of the plane and be non-aromatic, which isn't anti-aromatic, so it doesn't suck too bad, but like aromatic, right? That's so much better. So it's going to choose to suffer a tad and be aromatic. And like the scientific reason for that is the added stability from being aromatic kind of like makes up for the instability of being planar. And some nods, but some people were just like, I get it. It's a Monday. It's too early for this. But hopefully it's not like gibberish. All right, let me zoom out. Let's see if there's. All right, so any of the ones we didn't cover, is anyone like, I need to know how to do this one? Or are we okay with these guys? Yeah. I really wish. Look, I don't want to sound cocky. It's sometimes I sit in lecture and I'm like, oh, is that what we're doing today? Yes. No. So if they're sp2, they're each gonna donate 2 electrons. So 4 total, yeah. Then they donate 0. So anytime they're sp3, they're not donating any electrons. But really good question. Yes, we definitely can. First, I want to do this one. So I'm not going to help you. just going to ask you, what do we think of this? Okay, so instead ignore the double bond. That's a good one. Simon, what do you think? Yes, so in case anyone didn't hear him, the ketone is always just going to act like a carbocation because it's always going to be an sp2 carbon. And the electrons from the double bond are always going to move outward. They're never going to go into the ring. So it's always going to donate 0 electrons. Good question. Yes. Go ahead, answer it. Let me know.
5 electrons on it.
Why is it 4, not 5? So I think what you're doing, Eric, is you're counting the double bond as 2 and then adding the 1 for the nitrogen. The nitrogen is just like the double bond.
So
it's just 2 total, yeah. 1 from the carbon, 1 from the nitrogen.
Yeah, I'm counting.
Do you want to look at how he's counting it? Okay. I love when you guys help each other. It gives me so much serotonin. All right, so before you even count the electrons, is there anything here that maybe tells you anything? Yes? Yes, exactly. So I want you guys to take, I want you to use good test-taking strategies, okay? So when you see something like this, the first thing I want you to notice, wow, that's sp3. So that automatically means this is non-aromatic. YBE. Yes. Yes. Yeah. So, okay, that's a really, really good question, actually, and I do want to talk about that right quick. So the question was, if you didn't hear it, is conjugation strictly carbon atoms or can it have heteroatoms? So in general, conjugation can be anything that's sp2. So it can definitely count heteroatoms, positive charges, negative charges, radicals, all that kind of stuff. But in certain reactions, when we ask for like a conjugated diene or something, such as Diels-Alder, we're specifically looking for carbons because of the nature of the reaction. So like in Diels-Alder, conjugation only counts as carbons because if there was like a nitrogen here or something, that wouldn't react the same way. Does that answer your question? Hell yeah. I can ask and then we'll go back to you. Okay. Yes, what's up? Hell yeah. Yeah. Okay. Okay. So here's the thing. Yeah, that's a very valid question, and I'm pretty sure I know exactly what question you're talking about from the chapter 13 problems. So if they give you something like this, right? We have sp2, sp2, and then we have sp. Yikes, right? This is technically conjugated because it does have a p orbital, right? And so like the triple bond has 2 sets of p orbitals, right? One of them will be aligned, one of them won't be. So it kind of depends on the professor whether they want to say yes it counts or no it doesn't. So in general, what I told you guys is technically speaking, yes, this guy is conjugated or it can be conjugated, but for the purposes of this class, since neither professor talked about it, I'm going to say it's not going to show up on the exam. Okay. I don't promise anything, dude. With these, I was literally telling Katrina yesterday, I was like, I would have died this semester without you. I can't. Oh. That's all. So I'm going to actually show you some practice problems. I've been very distracted today. All right, so we're going to do the ones that are ugly because I want you to know what this means. What the heck is all of this stuff, right? He's just trying to be mean. So all of these things, they are exactly, they're just spectator ions, so we're just going to do one of these. Bam. Yeah, we just ignore them, right? It's just there to be annoying, just to confuse you. So the only reason they're there is they want to highlight the fact that this is negative, 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 positive. All right, so the question is asking you, say this, and I'm going to like bark at anyone who doesn't do this. When you're taking your exam, every single question, read it very carefully because he'll give you 3 in a row that's like aromatic, and then he'll be like non-aromatic, anti-aromatic, non-aromatic, and then you just keep going. You keep picking the aromatic ones, and I'm like, no. So keep that in your mind. So now let's really quick figure out which one of these is aromatic. What is the first thing you guys should see when you look at this? What's the first thing that sticks out to you? Okay. Conjugation. Why do you say conjugation? Okay, that's fine. So when I look at this, because I've stared at these molecules for like ever, right? The first thing I see is that guy. Yes. So that guy is disgusting. He's sp3. And sp3 means what? Non-aromatic. Cool, but we're looking for aromatic, so this one is automatically out. Yes. Yes, you're right, but what do you mean by numbers are off? What rule does it follow? Yes, exactly. Perfect. So this one has 8 electrons, which is the 4n rule. So that means it is anti-aromatic. Perfect. The second one, someone said this before, I don't know who it was. It's an 8-membered ring. So we have to decide whether or not it's planar. If it's non-planar, it's automatically non-aromatic. Cool. But if it's planar, it would have how many electrons? 10. Okay, so 10 pi electrons. Is that a multiple of 4? No. So this is aromatic. Cool. But so at this point, you would pick that one and move on. But since we're practicing, we're going to do the other two. So number 3, how many electrons does it have? 4. So that one is automatically anti-aromatic. And then what about the last one? That one is also 4. Cool. So the answer is yay. Yes. Okay, 1 second, everybody. I am literally deaf. Pause for 1 second. Yes. Yes. Yes, we are definitely going to do that. The last thing I want to show you guys before you head out, just really quick, because this is something that he likes to do to trick you. Where is it? Of course, I'm not going to find it. Okay, I'll just draw it for you. So let's say he gives you something like this. He'll give you something like this, right? All this means is that we have -1 charge, right? So that means it actually looks, or actually it'll be something like this. We're gonna add a pair of electrons. So, okay, if he gives it to you like this, the circle means that it's fully conjugated, right? So what you're gonna do is this is like this, and then this guy has to have a charge because it's fully conjugated. And if it's a -1 charge, that means this is a minus charge. If it was a +1 charge, it would look like this. Oh, nope. Like that. Yes, -1, give 2 electrons, +1, take away a pair of electrons. And if it was a radical, it would probably just be a dot instead of a charge. Because he hates you guys. Okay, I will see you guys. Bye-bye. I will be here for another minute or two if you have any questions. Yes. Yes. The one that we did or the other? This one? Oh, that's the other stuff. Okay. Yes. You want to do the double ring one? Like 2 double bonds? It could, but it's not going to be any special rule. So you would just do like the double on the outside is still like a cation, and then the double on the inside is just one bond. One electron. Oh, I see. So that probably won't happen just because I think that would not be like a correct number of bonds going on. But I will look into it. Welcome. Hello.
Hey, are you gonna send out